All right, so in the last video we talked about stress at a point. We were talking about just 2D for the most part now. And this gave us a normal stress component, sigma, and a shear component. Now, this came about from when we expose the surface. You actually get a complex distribution of the internal tractions. This is the forces, the tractions that the body to the right, opposing that the body to the left. You can look at each little differential traction. It has a component normal and perpendicular to the plane. Normal and in the plane. The component that's normal to the cut plane is normal stress. The component that's in the plane is shear stress. Again, remember, all both have units of force per area. Basically taking it so that they're intrinsic quantity. Materials will fail at a certain stress level regardless of the geometry. Depends on what's the stress point. That's where you initiate the failure. Okay. As I mentioned before, it's usually quite difficult to derive this complex distribution, so we tend to simplify them. And we are concerned most often in this class with the notion of average stress. Okay? And this turns out to be a lot easier. Actually, we're going to get the average stress from the internal reaction forces. And the internal reaction forces, we mentioned before, are kind of easy to deal with because they come right from the okay? All right. So where this comes about is all right, so let's look at the notion of average normal stress. So I'm going to put a little wiggle on it, okay? The average normal stress. If you think about it on this surface A, right? That's surface A. Average normal stress on that surface is the sum of the stresses over that surface divided by the surface area. So the sum is really an integral quantity, right? So we integrate over the area of the stresses at a point, the normal stresses at a point, the differential area. So that's the sum of all the stresses. This unit is now force. Force times the area times the area. And the average is then to divide that by actual area. All right. So this term down here is obviously just the area of the exposed surface. So that's this area. That area, cut area, exposed surface area. Okay, now what about this top quantity? What's that? Well, if you think about that, let's look at simple part and tension. Measurement of a component like this. And there's maybe an external load here applied P. This is the cut surface, right? So there's actually another one to the right that we're going to keep down. On this surface, we see the internal tractions. Let's just look at the normal ones. We'll probably have some parabolic distribution. That's the actual stress. Okay? Again, force. Well, you know, I didn't talk more. I should have talked in the last video about the units. Sloppy about that. Force per area, right? If we're in SI units, force per area is a Newton per meter squared, right? That's the basic unit of stress. Now, that is defined as a Pascal. PA is the symbol for Pascal. Now, Pascal is really small, so A lot of times we're not talking about Pascal. A Newton, you think about it, Newton's about the weight of an apple, and a meter squared is like the size of a table. The stress level of an apple distributed over the entire table, very small. Right? Usually, when we're talking about actual loads, we're talking about megapascals and something even gigapascals. We're talking about the strengths of certain materials. Okay? Those are more typical units. Mega 10 to the 6, giga 10 to the in English units or imperial units, basic unit of force is a pound, and unit of area is an inch squared. And this is called pound per square inch, or it's called PSI. Now, pound per square inch is a lot more than a pascal, about 1,000, on the order of 1,000 pascals per PSI. Now you're talking about 1 pound instead of being on a meter squared on an inch squared, so it's a much smaller area. A lot of times you'll see still things written in terms of KSI, which is 10 to the third PSI. That's 1,000 PSI. And sometimes people will talk about MSI, which is 10 to the sixth PSI, right? A mega PSI. So be careful about the units of lots of times. Those are the units that we're going to talk about. Pascals, PSI. Okay? So be clear about KSI as opposed to a kip, right? Kilowatt power, that's unit of force. KSI is unit of stress. All right, so back to this picture. We've taken the tensile test, we've exposed the surface. Here is some distribution of normal stresses. Now, if you look at this, right, the net force acting on this surface is the internal reaction force N. And so, although from equilibrium we can see that N equals P, we can also see that N has to equal, or it results from, the net effect of all this surface traction. So it's the integral over the area of that normal stress. That is N. So N really is a fictitious thing. The internal reaction force doesn't exist per se, but you can consider it as the combined effect of all the normal stresses acting on the surface. Similarly, V is the effect of all the shear stresses on that surface. So that's N. All right. And now we can immediately recognize that that's actually what's in the numerator here. So that's N. And then that tells us that the normal stress is N over N. All right? So the average normal stress is just the internal reaction force at that point divided by the area. Okay? A lot of times N is P, but be careful. When I talk about stress, when I talk about average stress or stress, we always talk about stress at a location, all right? At this cut, or so on. You need to make sure that the stress is always going to involve the calculation of the internal reaction forces at that location, not the external ones. Okay, I'll emphasize this several times. It's a mistake I see students make a lot. All right. So that is the average normal stress. Average normal stress. We can get the basic approach to getting this is you can get N from equations of equilibrium on the free body diagram. So for example, this was the problem. You can get N from the sum of forces, sum of moments. Once you know N, you know this cross-sectional area, right? Again, that area is the cut area. It's the exposed surface area. That's N. And then we get the average normal stress. Now, the average normal stress, right? Look at it. The surface. The average normal stress is as if there was a uniform distribution. Another way you can kind of think of it, this would be sigma bar. All right? If the actual distributed stress was uniform, then sigma, the stress at a point, would exactly be equal to at every point the average normal stress, right? In reality, it's typically not. You know, we might have a parabolic or some distribution, right? Call this the actual stress, right? And you can see what's going on here is at some points we're underestimating the value by considering, well, I should say this. At some points, here at the ends, the average normal stress is actually going to be higher than the actual stress. In some locations, it's going to be the other way. Actual stress might be higher than the average normal stress. I mean, that's the notion of an average, right? Some points are higher, some points are lower. It's an average, right? So there's a bit of an error that possibly happens here. Or I should say it this way. If you think about the failure of a component, it happens at a point. So really, the failure occurs as a result of actual stress at a point. When that exceeds some value, you usually see something of failure. But that's a little tricky to calculate directly. So we usually use the assumption that we're considering actually average normal stress. So this actually can be an underestimation of the actual maximum stress that occurs. Right? We'll talk about it later when we talk about factor of safety. There's something to do to try to compensate that factor. Another thing is also when you have stress concentration, these other things called stress concentration factors to try and correct for that. Now, we're going to consider geometries where this variation is not that big. And so looking at the average stress is a reasonable thing to do. There'll be some situations where that variation is quite large, and then we'll use things like stress concentration factors to try and compensate for that variation. Okay, so that's the average normal stress. The average shear stress is basically goes the same way. If you look at it. Go back to this. Oh, force like this. Right? And so this produces normal stress. Now let's just look at the shear stresses. There's actually some distribution of shear stresses on that base. You know, again, remember the actual traction. Something like that, right? But there's a normal, and then we're looking at the in-plane component, or the shear component, right? So this is actually tau is a function of position on that surface. Again, the surface we're talking about is this surface here. This is A. Right? Now, the net force acting on this, well, V, that's opposite of the normal convention. That's going to be the integration over that area of tau. Now again, we want to look at the average shear stress. The average shear stress is going to be the integral of tau dA. You can see it's just over the area. That's the average shear stress. It's similar to the average normal stress. It's just obviously a component. So we get that. Again, it can be lower than the actual in some locations and also higher than the actual in some locations. So V gives us the shear stress and N gives us the average normal stress. Now, from this point on, actually, if I call something stress, most likely I'm talking about the average stress, right? If I mean stress at a point, it'll actually be the stress at a point, all right? Okay. Maybe I should just do a quick example. Well, let's kind of redraw this part. So let's determine the average normal and shear stress at this point A. Okay? This is what that sort of graphic looks like. Okay, and let's just do some units of dimension. So let's say this is 100 pounds, call this 50 pounds, and then we'll get this here, 10 inches, okay, so in this case, actually I don't just need those so the average normal stress is N over A. Average shear stress. So what do we need to know? We need to know the normal component, the shear internal force. There's actually going to be a moment as well, but we don't really need to know that. We also need to know this area. So that's part of the part design. So let's say that this is 3 inches, and that this whole thing is 1/4 of an inch. Okay? So that means the area of this exposed surface here is going to be 3 inches times 1/4 inches. So that's inches squared. So it's 3/4 inches squared. So it's 0.75 inches squared. That's the cross section. All right. Now, if we do sum of forces in the x equals 0, that tells us from this free body diagram that N has to equal minus 100 pounds. And if we do sum of forces in the y direction equals 0, here at V, the way I've drawn it, V balanced out 50, so V equals 50 pounds. Right? So actually, we have 100 pounds acting this way, and a net pound of 50 pounds acting down this way on the face. All right? So this is actually what we would call the compression force acting on the face. Compression force tension force acting on. All right. So the average normal stress is going to be that N is minus 100 pounds over the area, which is 0.75 inches squared. So it's pounds per square inch, and this is going to be 400 over 3. So 1.3. So this is 133 psi. Okay. Now, for the normal stresses, it's really important that you get the sign correct. Right? For the shear stress, it's a little more tricky to ascertain the sign. It's not, there's a convention to it. But for now, I don't want to really worry about the sign convention on shear. Right? We'll talk about it. I'll do that later. This is fun. The shear is going to be 50 pounds over the 0.75, which is squared. Right? So that's going to be 4 times 50 over 3, so 200 divided by 3 meters. That's like 70. 73.3 psi or something like that. I'm actually really terrible at doing things like this. I should be better at it. Oh, I got this one. Oh, 66.6. obviously it's half of this. Okay. But anyway, that's the value, right? So that's the average normal and the average shear stress.